The magnetic pendulum is a demonstration of chaos. It consists of three magnets and a pendulum that is magnetic at the end. If we put the pendulum right above the red magnet, then predictably, it will come to rest right above the red magnet. However, if we shifted the initial position of the pendulum just a bit, then it will become incredibly hard to predict where the final position of the pendulum will be. Because of this, the magnetic pendulum is a demonstration of chaos. Chaos in physics occurs when a system has random or unpredictable behaviors, despite the fact that it has deterministic laws. The magnetic pendulum is chaotic because even though we can determine the outcome of certain initial positions, the further we stray from these initial positions, the more random and unpredictable the outcomes of this pendulum seem. In order to illustrate chaos, we created a code in order to map the trajectory and final position of the pendulum. We used our code in order to simulate the trajectory and final position of our pendulum with different starting positions. On our plots, you can see three blue circles, which represents the three base magnets, a red circle which represents the initial position of the pendulum, an orange square which represents the final position, and gray lines which represent the trajectory of the pendulum. In our first plot, we start our pendulum on the same axis as one of our magnets, or in other words, we start right in front of the top magnet. Predictably, the pendulum ends at the top magnet with a straightforward trajectory. However, if we were to shift the initial position of the pendulum very slightly to the left, then we can see that the pendulum will instead end on the bottom left magnet. Furthermore, the trajectory of our pendulum is way more chaotic than the trajectory of our pendulum on the last plot. Going even further, if we were to shift the initial position of the pendulum slightly up, we will see that we will get a completely different trajectory, and this time our pendulum will end on the magnet on the bottom right. Despite having relatively close initial positions, the outcome of each simulation were strikingly different to each other, thus showing the chaotic nature of this system. If we were to use a code like ours to map the final position over a range of initial starting positions, we can then create fractal-like diagrams, thus adding to the chaotic nature of the magnetic pendulum. So what I have here open is an application that basically showcases these fractals. And you can download this application on your own computer. I'll go ahead and put the link in the end of this video, and this is also where some of the images of this video will be coming from. So right here, we have these three dots. This green, red, and blue dot are the position of the base magnet. And my cursor is the initial position of the pendulum. So if I were to put my cursor on any one of these colors, basically these colors correspond to the final position where the pendulum will end up at. So we put our cursor on this red area right here. We see that it wants to go to the red magnet. Now, if we were to put our cursor on this this green area here, we see that despite being closer to the red magnet, the pendulum will end up at the green magnet because of the magnetic field is stronger here. Now, because this is fractal-like, the amazing thing about this is that if we were to go in between the blue and the red, the blue and the red and the green, there's also an area which is blue as well. Yeah, let me see if I can put my cursor there, and as you can see here, in between this area where it's red and green is actually blue, and it wants to go to the blue magnet. So that's the amazing thing about this program. This is a great program that showcases these fractals. You can actually make your own designs with this as well. And overall, it's a very great program to get a second look at these fractals and these how these pendulums work. So go ahead and check it out. Overall, the magnetic pendulum is a great and interesting demonstration of chaos that I'd encourage anybody at home to look more into. Thanks for watching this video, and gig 'em.